Welcome to the next lecture in electric circuit analysis. We were discussing the Laplace transform, and in this particular lecture we are going to focus on the circuit analysis using Laplace transform. So Laplace transform, we have seen that is the most powerful mathematical tool that can be used for circuit analysis, circuit synthesis and the design of the circuit. Generally we come across a term which is known as the system. The meaning of system is a mathematical model of any physical process that relates the input to the output. So we can say that if any physical system is represented by a black box which is given by G, then the relationship between input and output is said to be that system. So input or the excitation will be there, output or response will be there for the measurement, then that is known as the system. When we talk about the circuits, they are nothing but a class of electrical systems. So because the physical process may be a combination of too many factors, so the combination of class of systems lead to the formation of the circuits. Laplace transform, we have already seen in the previous lecture, has two important characteristics which makes it to be an attractive tool for the circuit analysis. So these characteristics are: the transform can be set of linear constant coefficient differential equation into a set of linear polynomial equation which is easier to manipulate. So we have seen that in the time domain we were operating the system with the differential equation. Now we can have the polynomial equation which are linear and algebraic. Also, the initial values can be automatically introduced into the polynomial equations. These initial values are due to the current and the voltage which are present in the inductor and the capacitor. So initial conditions are inherent part of the transform process. We need not to take the initial conditions separately, rather than they are automatically present in the system. Now let us see the circuit analysis graphically, how can be solved with Laplace transform. So if we have any system which is given by the linear circuit, and the time domain response we have to find out for a linear system which comprise of inductors, capacitors and resistors, that is the first order circuit and the second order circuit, then we can write those differential equations and use the classical techniques to determine the response waveform or the output. So here we get the classical solution method by which we can get the output or the response from the input. However, if we go in the S domain, which is the frequency domain, then the differential equations what we have is converted to the Laplace transform, and then we get algebraic equation, and algebraic techniques are being used to determine the response, and then through inverse Laplace transform we can get the response in the time domain. So we transform the circuit from the time domain to the S domain. So S domain is nothing but the Laplace domain or the frequency domain. We solve the circuit using any circuit analysis technique that we have studied during our theorem classes, and then we take the inverse Laplace transform to get the solution in the time domain. So these are basically the three important steps that we follow for the Laplace transform solution for any circuit. Now we see how do the circuit elements are represented in the frequency domain. For example, in the time domain, from the Ohm's law, we have the relationship between the voltage and the current for a resistor is given by V of t is equal to R I of t. This can be represented in the frequency domain or the S domain as V of s is equal to R into I of s, where R is basically the resistor that is present in the network. So the current which was in the time domain given by I of t has been converted to I of s, and the voltage which is in the time domain is V of t is converted to V of s. Now for a resistor this is very simple to convert. Now coming to the inductor, if we have inductor in a system which is having the excitation voltage as V of t, drawing a current I of t, then the Laplace transform of V of t is equal to V of s. The Laplace transform of I of t is I of s. The inductor will be converted into an inductor with a voltage source, because the initial current in the inductor is I of 0, which can be written as L into I of 0 minus, and the inductor L will be replaced with S into L, because we have the current dot or the differential in the time domain. So in order to take the account of di by dt, we convert that in frequency domain by S. So this is a representation in the form of the voltage source. If we take the current source into account and we try to represent as source transformation, then we have inductor SL in parallel with a current source, which is given by I of 0 minus divided by S. So we see that the initial conditions are well taken into account in the Laplace domain, and in the time domain we write the voltage across the inductor in the time domain is equal to L into I dot or L into di by dt. Now if I convert that into the S domain or the frequency domain, I'll get the solution for the voltage as S into L I of S minus L of I of 0. And if we need to determine the current, which is the voltage divided by the net impedance forming the inductor plus I of 0 minus by S. So this is the initial current which is present in the inductor, and this current is coming due to the potential difference across the inductor. Similar to the inductor, we can have for the capacitor. So capacitor is having the initial voltage V of 0, which can be represented as V of 0 by S with a voltage source in series with the inductor capacitor, which is 1 by SC, to represent in the form of a voltage. If we want to represent the capacitor in parallel with a current source for the source transformation, we will have C of V of 0, which represent the initial current, and 1 by SC represent the capacitance in the frequency domain. So we know that the current flowing through the capacitor is given by C dV by dt, which is in the time domain, and the current and voltage in the frequency domain can be written as SC V of S minus C of V of 0 minus, this is the current, and the voltage will have the two terms. The initial voltage is V of 0 minus by S, and here the voltage equation will get I of S by SC. So capacitor in the frequency domain we have represent to take into account the current and the voltage. Now let us assume the zero initial condition for the inductor and capacitor. Then in that case, how do we represent the time domain and frequency domain relationship with zero initial condition? Because mostly we deal with the problem for zero initial condition. In that case, for the resistor, inductor and capacitor, the voltage relationship, voltage current relationship is given by, so this is very straightforward in accordance with Ohm's law, is V of S is equal to R into I of S. This is V of S equal to SL I of S for the inductor, and the capacitor Vs is equal to 1 by SC I of S. Generally, we can remember one particular equation is voltage is equal to the current multiplied with the impedance. So impedance can be for the resistor as R, for the inductor we will have XL, and for the capacitor we can have XC as the inductive reactance and capacitive reactance. Now inductive reactance XL is equal to omega L, and capacitive reactance is equal to omega 1 by omega C. Generally, we write the omega is S equal to J omega T. So we can convert that from the time domain to frequency domain. Generally, we find the impedance as the ratio of voltage by current. So from these relationship, if we determine the voltage by current relationship, then we get for the resistance, reactance and the capacitance relationship for the resistor, inductor and capacitor. So resistor do not change in the time domain and frequency domain. Inductor change from L to SL and capacitor change from C to 1 by SC. So we can take into account the current voltage relationship by converting the time domain to the frequency domain. So Laplace transform in circuit analysis facilitates the use of various signal sources such as impulse, step, ramp, exponential, and sinusoidal. So the given input signal that we have can be in the form of an impulse signal or step signal, ramp, exponential, sinusoidal. So a lot of signals or the combination of the signals can be there. We can take the Laplace transform of that. Let us solve one problem. Find V naught of t. So we need to determine what is the output voltage V naught across the 1 Henry inductor, and we have to assume the zero initial conditions, means there is no current which is present in the inductor initially, there is no voltage which is present for the capacitor, and the input, if you see, is a step input u of t, and there are resistors in the network. Now this network is in the time domain. So if we need to convert this network in frequency domain, then we know that u of t, which is the step input in time domain, will give 1 by s in the frequency domain. So we have transformed the source in the frequency domain. Now the inductor of 1 Henry will be represented with s into L, which is s, and the capacitor of 1 by 3 farad will be changing to 1 by SC, so that is equal to 3 by S. Resistor remain the same as it is. There is no change in the resistor, and we can solve this using any circuit analysis technique by mesh analysis or nodal analysis. If we solve this problem using mesh analysis, we can take two current or two mesh current in the frequency domain, and we can write the KVL equation for this mesh 1 and the KVL equation for the mesh 2. So we can write the equation KVL equation 1 and KVL equation 2 in the mesh 1 and 2 and determine the unknown currents. So here the unknown current will be I1 and I2, which are in the frequency domain. So once we have solved the variables, we can determine the voltage V0, which is the output quantity that we have to determine, as S into I2, because S is the XL value, so XL is equal to S, and the current which is flowing through it is I2. So S into I2 will give me this relationship. Now this is the equation as a function of S. We have seen in the previous lecture how to break down the partial differential equation to get the solution in the frequent time domain. So the time domain counterpart, which is inverse Laplace transform, how to compute the inverse Laplace transform we have discussed in the previous lecture series. So here it will be 3 by root 2 e to the power minus 4t sine under root 2 t volt, and for all t greater than equal to 0. So given a problem in time domain, we have converted it into frequency domain circuit and then apply the normal circuit analysis technique, and then through inverse Laplace transform we have obtained the solution of V0 of. So we have avoided writing the differential equation for the inductors and the capacitors. Next problem, where we need to determine the V0 of t, assuming that the initial voltage is 5 volt across the capacitor. So we have a capacitor here 0.1 farad and the initial voltage is 5 volt. If you see the input, it is 10 e to the power minus t u of t. So it is a summation of the step input and the exponential input. So we have seen that in Laplace transform we can deal with any type of input that is present in the system. We have also a current signal in the form of impulse to del of t. So del of t represents the impulse current. So how to deal with this type of signal? So again, the time domain circuit we will be converting to frequency domain, taking the Laplace transform of the input source, which is equal to 10 by s plus 1. The Laplace transform of the current source is 2 ampere, and we can represent the capacitor with the initial condition. So the capacitor 0.1 farad can be represented as 10 by s with the initial current of 0.5 ampere, because the voltage is given 5 volt, which can be obtained as the initial current as 0.5 ampere, given we know that the current is equal to C into V. So we have converted the time domain circuit in the frequency domain. Now we can apply any technique. So let us solve this problem by nodal analysis, applying the KCL equation at the node V0 of S, which is my unknown variable. So I'll write the KCL equation at this particular node and try to determine the voltage V0 at the node. So we have determined the voltage at the node by writing the KCL equation, which I can split up to find the constants A and B that we have learned in the previous lecture, how to determine the constants A and B by splitting the equation. So A is 10 and B is 15, which I can put it in the value of V0 of S, and then taking the inverse Laplace transform. So here we have inverse Laplace transform, will get V0 of t in the time domain. So again, this problem is solved from the time domain to frequency domain conversion and back transform to the time domain by taking the inverse Laplace transform. One more problem let us see, where we need to determine the capacitor voltage Vc of t. This capacitor is there, assuming that the input voltage Vs of t is 10 u of t and the current which is present in the inductor at zeroth condition is minus 1 ampere and the voltage which is present across the capacitor is 5 volt at the initial condition for t equal to 0. How do we determine the capacitor voltage? So again, this circuit will be broke up into the frequency domain where the input voltage will be converted to the frequency domain as 10 by s, because 10 u of t will give me the Laplace transform as 10 by s, and the inductor circuit will be obtained as one inductor which is in parallel with the current source, and the capacitor can be represented as one capacitor in series with the voltage source, considering the initial current and the initial voltage. Once we have obtained the frequency domain circuit, we can apply the nodal analysis or the KCL equation we can write at this particular node, the equation, and we can determine the voltage V1, which is my unknown quantity. So we have taken the nodal analysis to determine the node voltage, which is my unknown, and then we can have L inverse, that is the Laplace inverse, we can find out to find the voltage. So previous lecture we have discussed this, how to obtain the solution in the Laplace transform and how to find the inverse Laplace transform so that we can get the solution function of t in the time domain. Now, one problem that is solved for Thevenin's theorem, where we need to determine the output voltage V0 of S, that is the voltage across the resistor, assuming no initial conditions, means there will be no energy stored in the inductor or the capacitor, and the current which is the driving excitation source is 10 u of t. Now we have a dependent source here in the circuit, dependent voltage source, where Ix is the current which is drawn by the 2 Henry inductor. Now to apply Thevenin's theorem, we need to determine the Thevenin's voltage first. So Thevenin's voltage is the voltage which is open circuit at the load terminal. So we are considering the 5 ohm as the load terminal, RL, which will be open circuited. So once we have open circuited, no current will be flowing here, so Ix will be 0. Then 2Ix term will be 0, means it will be short circuit. We can determine the open circuit voltage by any principle. Here no current is flowing, so the entire current 10 by S will be flowing this side, and we get the voltage 5 ohm resistor multiplied with the current. Ohm's law will get 50 by S as the Thevenin's voltage. Thevenin resistance we can find out by the concept of, or Thevenin's impedance we can find out by the concept of Thevenin's voltage by Norton current. So we know that Z Thevenin is equal to the Thevenin voltage by the Norton current, or we can say that it is equal to open circuit voltage by short circuit current. So once we have sought the terminal AB, what is the current which is flowing through it, ISC, that we have to find out. And in order to find out ISC, we can apply any theorem which are known to us. So we have applied here the concept of nodal analysis using multiple steps. For example, what is the current flowing Ix? So current Ix is basically the voltage divided by the impedance 2S. So this is equal to XL value, because the voltage V1 we have taken as a known variable at this particular node. Now we can apply the nodal analysis to write the equation, and we can determine what is the value of V1. Similarly, we can find what is IS. Now once we divide the open circuit voltage by short circuit current, we'll get the Thevenin impedance. Once we get the Thevenin's voltage and Thevenin's impedance, we can reconnect our 5 ohm resistor which was replaced from the network, And now using the voltage division rule, we can find what is V naught, which is from the voltage division rule we can find out, and the answer is 125 by s plus 4. However, this is in the time domain. We can find in the frequency domain. This is in the frequency domain. We can find using the Laplace transform to get the equation in the time domain. So we'll get in the time domain what is the voltage across the 5 ohm resistor by taking the inverse Laplace transform of V naught of s. So the answer is 31.25 1 minus e to the power minus 4t u of t volt. So this complete the lecture on circuit analysis using Laplace transform. So both lecture 13 as well as lecture 14 are very important, which cover the entire concept of frequency domain solution for the Laplace network solution, how to solve the circuit problem using Laplace in the frequency domain. Thank you for now. See you in the next lecture.